Right. So in this video, we are going to I'm going to introduce you to the concepts of a determinant of a matrix, and then we will move into defining what an inverse matrix is. Right. So determinants and inverse matrices are defined only for square matrices. Right. So when you have a square matrix, there's this thing called determinant. Right. So determinant is merely a number, a real number assigned to a matrix. That's all you need to know. So there's a deeper meaning to it, but in your scope, that's all you need to know. Determinant is just a number. It's just a number that is assigned, uniquely assigned to a matrix, a square matrix. So determinant is a number that is uniquely assigned to the matrix. So this only works for square matrices. So how do you, what is the notation of a determinant? If A is a square matrix, then its determinant is written as this: det A, or simply just write the matrix and put these absolute signs, right? So remember absolute signs, absolute value of a number. So this is the modulus, right? So you put the modulus A. This refers to the determinant. Now in your scope, we will only learn how to find the determinant of 2 by 2 matrices, right? So in your scope, only determinants of 2 by 2 matrices will be studied. Only 2 by 2 matrix. This is the easiest case. So we can find the determinant for a 3 by 3 matrix, 4 by 4 matrix. So that will be done in university level courses, but in your A level course we will only focus on 2 by 2 matrices, right? So that's the easiest. Okay. Now let's see how to calculate the determinant. Right. So given a matrix like this, 2 by 2 matrix, A, B, C, D, then its determinant of the matrix is calculated like this. First multiply the diagonal elements. First multiply the leading diagonal elements, that would be A into D. A, D. Then put minus sign. Put minus. Then multiply these two. Right? C and B. C, B. That's it. That's how we find the determinant. Right? This is the determinant. But you can do a lot with this. That's the thing. So let's look at some examples. Suppose A is 1, 2, 4 and 3. Then can you guess the determinant? First 1 into 2 is 2, then put minus 3 into 4, that is 12. So the determinant is minus 10. So notice here, it looks like the absolute sign, but it's not actually the absolute value of A. It has nothing to do with absolute values. Why I say that? You can get negative values as well. Right? So negative values can be there. This is called the determinant. Right? Or you could write det A. Det A is also minus 10. Right. Another example, B minus 1, minus 2, 3, minus 4. Determinant of B. These two, first multiply these two. Minus 1 into minus 2. Minus 1 into minus 2. Then put minus sign. Minus 4 into plus 3. Minus into minus, that is 2. This is minus, this would be minus 12. This is 2 plus 12, the answer is 40. See how easy this is? It's very easy. Right, so I will give you guys some exercise and I want you to find the determinant of these matrices. Right, so find the determinant of these 3 matrices. Right, so find them and see what will happen. Right. So now we can begin the definition of inverse matrix. Now, when it comes to numbers, you have learned about division. So until now, we learned about addition, scalar multiplication, subtraction, multiplication of two matrices, and we can't define division for matrices. So instead of division, we define an inverse. For example, you can see that A inverse means 1 over A. So 1 divided by A. Right? 3 inverse means 1 over 3. Right? So it's actually not inverse, 3 minus 1. So it's actually 1 over 3. And this is A minus 1, 1 over A. Right. So don't confuse this with sine inverse, tan inverse, those things. Do not confuse that with these. Right. Here's the thing. So if A is a square invertible matrix, invertible means if you can define an inverse for it. So that's why it is called invertible matrix. So we'll learn what this is later. Then inverse of A is written like this: A inverse. Okay, is the inverse of matrix A. So that is the notation. This is just the notation. Now here's the thing. If you divide A by A, what is the answer? That is equal to 1. So if you divide 3 by 3, the answer is equal to 1. Now I can write it like this: A into 1 over A must be equal to 1. So what is this? Reciprocal of A. So let me take the reciprocal, then this is A minus 1. Right. So what does that mean? A multiplied by A to the power minus 1 must be equal to 1. Right. Okay. So when it comes to, this is how we find actually inverse of a matrix. When you multiply a matrix by another matrix, if the answer is not 1, if the answer is the identity matrix. Now in matrix universe, you don't have 1 there or unity. You have an identity matrix. So what is an identity matrix? Remember, I2 is 1, 1, 0, 0. Then I3 is, these are identity matrix: 1, 0, 0, 0, 1, 0, 0, 0, 1. These are called identity matrix. Matrix universe එකේ මේවා තමයි 1, 1. So they have this property: when you multiply A by A inverse, then the answer is I. Right? Or when you multiply A inverse by A, the answer is also I. Right? This has this property, very important property. So we will use this to get rid of matrices. If you want to get rid of a matrix from one side, then you are going to multiply that equation by the inverse of that matrix. Right? Inverse of that matrix. Right? So this is very important. Now how do you find the inverse of a matrix? If A is given, right, then when you multiply that matrix by another matrix, then the multiplication should be equal to I. Right? So this may not make any sense to you. Now how do you find the inverse of a matrix? So let's get into that without any details. So the shortest way to find an inverse is this. For example, let's say this is A, matrix A, B, C and D. Right? First thing you find is determinant A. So A determinant is AD minus BC. This is the determinant of A. This is why we learn determinant before the inverse of a matrix. Then how do you get the A inverse? This is what you do. A inverse is equal to, you write the matrix. All you do is You see the diagonal elements, you change the locations. Right? You swap these two elements. So D goes to top and A goes to the bottom. That's the first thing you do. You change the position of the diagonal elements. Then multiply the other two elements by minus. That's it. Minus B minus C. So this is actually called the adjoint of a matrix A. This is not the inverse. This is not the inverse of A. This is called the adjoint of A. Now we have to do one more thing, that is to multiply this by 1 over determinant A. Now here's the thing, this is not a matrix. A determinant is a number. Determinants merely a number. So you can divide or multiply by a number, right? Okay. So 1 over determinant A multiplied by this. This is called actually the adjoint of it. So let me go through that again. When you want to find A inverse, then what you're going to do is, first you find the determinant, right? Then 1 over det A, then write down the matrix. What you're going to do, you're going to swap these two elements. A goes here and D goes here, right? Then multiply each the other two elements by negative sign or negative 1. That's all. Now notice here, this you have a division by a number. So you have to make sure that the determinant of a matrix is not t equal to 0. So that's the only thing. So all square matrices do not have inverses, right? So those who have inverse will have a determinant non-zero, right? Non-zero determinant. So let's put a note on that, right? So only square matrices can be invertible. So there's a possibility. You can. There's a chance that you will find an inverse of a matrix or may not. A matrix has an inverse if and only if. So you saw that when you determine the inverse of a matrix, you divide that by the determinant A. So its determinant is non-zero. If and only if the determinant is non-zero, then only you can find the inverse of a matrix. So there's a test for it. We can use this test. So if a matrix is given, if they ask you to find the determinant of these matrices, so to make sure that these have inverse or not, then all you do is find the determinant of the matrix and show that it's non-zero. If it is non-zero, they have inverses. If it is 0, then it will not have an inverse. So if A inverse exists, then determinant A is non-zero. It goes both ways. If determinant of A is non-zero, then A inverse exists. So matrices that has inverse is called non-singular matrices, right? So matrices that does not have an inverse is called singular matrices, right? So singularity and non-singularity deals with the determinant of A. So for non-singular matrix, determinant of A is non-zero. For singular matrix, determinant of A is 0. Right, so let's do an example. Let's find the inverse of these three matrices. It's very simple. So when a matrix is given, first find the determinant of the matrix. Right. So let's take this matrix. So what is the determinant? A determinant is 3 into 5 is 15 minus 2 into minus is minus 2. So determinant is 70. Right, this is non-zero, which means we can find the inverse. Therefore, so this implies A inverse is 1 over 17. Then put the 2 by 2 matrix. All you do, change the positions 5, 3. Change the sign. This is minus 1, so it should be plus 1. Plus 2 becomes minus 2. Very easy. Next, B. First find the determinant, B det. Minus 2 into minus 2 is 4 minus 1 into minus 1 is plus 1. The answer is 3. So this is non-zero, which means matrix B is invertible. So B inverse is 1 over 3. Then change the position. Minus 2, minus 2. It's the same thing. Does not change. This becomes plus 1. This becomes plus 1. 1, 1. Right. And finally, determinant of C. So what will you get? 1 into 2 is 2. Minus 1 into 2 is 2. The answer is C. So, no inverse. Right. So, C is non-invertible or it's a singular matrix. So, that's how we determine the inverse of a 2 by 2 matrix. This is very simple. So, we're going to use this to find solutions for linear equations, system of linear equations. So for you guys, we only solve simultaneous equations, right? Simultaneous equations of two linear equations. So that's what we are going to show you how to solve. So in the next video, we will see how two simultaneous equations are solved using matrices.